This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss question bank on Module 2 Quantum Mechanics. And in this presentation, I will discuss the second part of long answer questions, part B. Okay, so the earlier 11 questions I have discussed in the earlier presentation. So 11th question is that show that the energies of a particle confined between two rigid walls of infinite potential are quantized. So we have to show that a particle that is trapped in infinite potential well, the energies are quantized. Okay, so that is what we need to show. Okay, so this kind of problem we have already solved earlier. So first we need to start with Schrodinger wave equation. We can draw this particle in one-dimensional box, right? So they have asked us to discuss the energies quantized in. So this is a particle that is trapped in this infinite potential well of width x is equal to 0 and x equal to a. So the length of the box is a. So this is in only one dimension, and the particle, this is the particle that is trapped in infinite potential well, and where the potential is 0 inside the box. That means particle is free inside the box, so it can freely move inside the box, and at the boundaries the potential is infinite. That is why we are saying that the particle is trapped in infinite potential well, because it is trapped inside. Inside it can move freely, but it is not able to, it cannot cross this box, or it cannot cross the boundaries, because the potential is infinite at the boundaries. Okay, so for such a particle which is trapped in this infinite potential well, we need to show that the energies are quantized. That means the energies are discretized. Okay. So how do we show that the energies of this particle are discretized or quantized? We need to solve the Schrodinger wave equation. Okay. So this is a Schrodinger wave equation. Rho space I by dou x square plus 2m into E minus V. This is not velocity, this is potential, right? So that potential that we are discussing here, so that is V. 2m E minus V by h cut square into psi is equal to 0. So this is the Schrodinger wave equation in one dimensions. So we know that the potential is 0 inside the well. So by substituting V is equal 0 in Schrodinger wave equation, we get this equation. Okay. So this is a second order differential equation. Okay. So the solutions of the second order differential equations are of this form. So you can think of this as b square plus k square, where I am defining this whole term as k square, right? So k square into psi is equal to 0. This is the second order differential equation. I am trying to solve this and find the roots. So then d square is equal to minus k square, or d is equal to plus or minus ik. Okay. So these are the roots. So with these roots you can write the solution psi of x is a sin kx plus b cos kx. Or you can write in the form in terms of exponential, a e power ikx plus b e power minus ikx. So here I am using this kind of form. Okay, so we can use any one of the form. Using both forms we can show, or we can find the energies of the particle is quantized. Okay, so yeah, once we get the solution, which is a wave function. Okay, so I am going to find out these unknown constants, right? I am going to find out these unknown constants A and B. To find these unknown constants, I am going to use the periodic boundary conditions. Okay, so these are the boundary conditions. Okay, boundary conditions. The boundary conditions, what do you mean by boundary condition? The boundary condition says that the wave function at x equals 0 boundary and x equal to a boundary must vanish, whatever it can be inside, but the wave function must vanish at the boundaries. So psi of x must be equal to 0 at x equals 0, and psi of x must be equal to 0 at x equal to a. So these are the two boundary conditions. So by substituting this first boundary condition in the solution of psi equation 4, we get, okay, psi of x is equal to 0, a sin k x equal to 0 plus b cos k x equals 0. So sin k is 0, cos 0 is 1, sin 0 is 0 and cos 0 is 1. So b is equal to 0. So we got one unknown constant. Okay, next we are going to substitute the second periodic boundary condition. So by substituting this, psi of x is equal to 0, a sin ka plus b cos ka is equal to 0, but B is already 0. So we don't have this term, we have only A sin K is equal to 0. A sin K is equal to 0, either A can be 0 or sin K A can be 0. If you take A is equal to 0, then A is equal to 0, B is equal to 0. That means if you substitute A is equal to 0, B is equal to 0 in equation, psi will be 0. Okay. We do not want to take A is equal to 0 because psi wave function will be 0. So we are taking sin K is equal to 0. Okay. So by taking sin K is equal to 0, we can find out the value of K, because sine of x is equal to 0 only for certain values, right? Sine of x is equal to 0 only for x is equal to n pi, where x is k. So k is must be equal to n pi, or k is equal to n pi by a. Okay. So now we got the value of k. Okay. So now this is what the wave function we got. Psi of x is equal to a sine kx. So but k value is n pi by a. Okay. So now we are going to differentiate this equation twice. Okay. So in the first, here also there might be a doubt that so there is no doubt here, but yeah. So here we are going to differentiate this equation twice. Okay. By differentiating the equation twice, we are going to end up with this equation. Okay. So comparing equation 6 and equation 3. Okay. Equation 6 and equation 6, if we compare, we will get these two terms. So equation 6 is this, 3 is this, dou square psi by dou x square plus 2me by h cut square into psi is equal to 0. So this is equation 3, and equation 6 is dou square psi by dou x square plus n square pi square by h cut square into psi is equal to 0. Okay, so these two equations are same except these two free factors are different. So we must these two factors must be equal. So 2me by h cut square must be equal to n square pi square by a square. So by equating this, we will get the energies. En is equal to n square pi square h cut square by 2me square. Or h cut square is nothing but h cut is nothing but h by 2 pi. Or h cut square is nothing but h square by 4 pi square. Okay. So by substituting that, pi will cancel out, we will get n square h square by 8m a square. Okay. So now the energies of the particle are discretized because these energies are not continuous. See, by taking n is equal to 1, we get E1, which is h square by 8m a square. By taking n is equal to, we get E2, which is 4h square by 8m a square. Okay, so the particle that is trapped in an infinite potential well, the energies of such a trapped particle are quantized. That is what we have proved. So the second question, what is de Broglie wave? Derive expression for de Broglie wavelength associated with a particle having mass m and velocity v. Okay, so de Broglie wave is the matter wave associated with a particle, and that tells us about the probability of finding the particle at a position in a given region of space. De Broglie wave is nothing but the probability wave or matter wave. Okay, so that is associated with a particle. It is going to tell us about what is the probability of finding the particle in a certain location in a box. So this is the particle trapped in this box between x is equal to 0 and x equal to a. This de Broglie wave or matter wave will tell us at this location what is the probability of finding the particle. At this location, what is the probability of finding the particle. Okay, so de Broglie wave or matter wave tell us about the probability of finding the particle at a position in given space. We need to derive the equation for the de Broglie wavelength. Okay, so to derive the de Broglie wavelength, I am going to use the Planck's theory of radiation. Okay, using the Planck's theory, I am going to write the energy of a photon or energy of a particle, which is energy of a photon is h nu, which is equal to hc by lambda, where nu is frequency is written as c by lambda. So nu is frequency. Okay, c is velocity of light and lambda is wavelength. Now, using Einstein energy mass relation, we know that E is equal to mc square. Okay, so this is equation 1 and this is equation 2. By equating these two equations, E is equal to mc square. Both equations are for energy. Okay, so by equating these two equations, we will get lambda is equal to h by m into c. Okay, so this is the wavelength associated with a photon. For a general particle, velocity is v, so I can write this equation as lambda is equal to h by m into v for a general particle, where m into v is momentum. So I can write lambda is equal to h by mv or h by p. Okay, so this is the de Broglie wavelength associated with a particle of mass m and velocity v. So we have defined what is a de Broglie wave, and then we have also derived the equation for de Broglie wavelength associated with a particle of mass m and velocity v. Next question, discuss different phenomena that show the behavior of light radiation interacting with matter. So we have to discuss about different phenomena that are going to show that light radiation interacting with matter. Okay. Behavior of light radiation interacting with matter, different phenomena. So we are going to discuss about 3 different phenomena, starting with black body radiation. Okay, black body radiation and photoelectric effect. And the third one is atomic stability. So in these 3 phenomena, we are going to discuss about how light is going to interact with matter and how does it behave when light interacts with matter, radiation. Okay, so we are going to discuss about these 3 phenomena to answer this question. Okay, first let us start with black body radiation. We know black body is a material object that absorbs all the radiation falling on it and it appears black. Okay, so black body is a perfect observer as well as perfect emitter of radiation. So when you supply energy, it will absorb all the radiation, and when you heat the black body, it is going to emit all the radiation. So that is why we call it as perfect observer as well as perfect emitter. But in general, object will not absorb all the radiation, it will not emit all the radiation, only black body does it. So how are you going to construct such a black body? So we are going to take a hollow cavity. Okay, so some material which has free space inside. So this is hollow space, hollow cavity. This is hollow cavity, and with internal walls are perfectly that reflect the perfect electromagnetic radiation. So we are going to make sure that the radiation, the walls of this hollow cavity are such that they are going to reflect the radiation. Okay, so they are going to reflect the radiation, and it has a small hole on the surface. Okay, so this radiation, the radiation that is entered through this hole gets completely absorbed due to successive reflection, because once the light through this hole, we are going to send the light inside, and this light is going to get absorbed at each reflection. Okay, so some of the energy is absorbed at each reflection. So successively, all the radiation that is falling on this walls of the black body is getting absorbed through these successive reflections. So once it absorbs all the radiation, we are going to heat this black body, and then the hole behaves as a perfect emitter when this cavity is heated to a temperature T, and eventually it begins to glow as the temperature increases. Okay, so when we heat this black body, it is going to emit the radiation, and we are Planck's measured this energy, radiation or heat energy emitted by the black body at each temperature versus different frequencies. Okay, so yeah, so this is heat energy. So small u is heat energy, and x-axis is frequency. So heat energy emitted by black body over different frequencies at a temperature T is equal to 2000, 3000, 4000 and 5000. So they found that the heat energy that is emitted by black body, for example at 2000 Kelvin, has a continuous distribution, and at 3000 has continuous, 4000 continuous and 5000 continuous distribution. So the heat energy that is emitted by black body has a continuous distribution over all the frequencies. Okay, this experimental fact is not explained by any theoretical predictions. For example, Stephen Boltzmann law or Wien's law, Rayleigh-Jeans law. So Wien's law could explain only this part and this part. Rayleigh-Jeans could explain this part, this side perfectly, but not the other side. Okay, so these theoretical predictions are not able to compare. We are not able to compare the theoretical equations with the experimental continuous distribution. So Planck has to come up with his own idea that in these theoretical equations, they are using that radiation as a continuous wave. They are treating radiation as a wave. By treating radiation as a wave, they are not able to explain the black body radiation experimental results. So then Planck came up with his own idea and he postulated that energy of radiation emitted by this black body is not a continuous wave. Instead, it is a discrete energy packets. Okay, E is equal to h nu, where h nu is the energy packet is called photon or quanta. Okay. So the energy that is emitted by the black body is not a continuous wave. Instead, it is as a energy packets, and each packet has energy h nu, and this packet is called as quanta or photon. Okay. So then he derived an equation using this idea, and whatever his equation is predicting is exactly matching with his theory. Okay. So Planck could explain his own experiment with his theory that don't treat radiation as a wave that we do in classical physics. Now the new idea is that we are going to treat radiation as set of energy packets or particles. So that is a new idea which gave birth to the new branch of physics called quantum physics. Came with this new idea of an energy packet which is called as quanta. Okay. So this is the first explanation for black body radiation experimental result, using the idea that radiation can behave like a set of energy packets called as quanta. Okay. So following the next black body radiation, the next experiment is photoelectric effect. This experiment is done by Hertz. Okay. So in his experiment, Hertz did irradiated a metal with light, and he found that electrons are ejected. When he irradiated light on a metal, he found electrons are getting ejected. And the observations from his experiment is that if frequency of incident radiation is smaller than the threshold frequency, no electrons are ejected. But if the frequency is greater than the threshold frequency of the incident radiation is greater than the threshold frequency, number of electrons are ejected, and the kinetic energy is linearly depending on the frequency of the incident radiation. Okay, so kinetic energy is linearly depending on the frequency of the incident radiation. So these experimental results could not be explained by classical physics. So these are some of the reasons. So then following Planck's Planck's idea, Einstein assumed, so the Hertz experiment is explained by Einstein theory. So Einstein assumed that light is made up of particles and each carrying an energy h nu called photon. Okay, so when a beam of light of an frequency nu is incident on a metal, each photon transmits all its energy h nu to an electron near the surface, and the photon is absorbed completely by the electron, and the electron thus absorbs energy only in packets of quanta, irrespective of the incident radiation. So the total energy that is absorbed by the electron is h nu, and when h nu is greater than the work function W, what is the work function? Energy required to dislodge electron, or electron is on the surface of the metal, and if the electron wants to come out of the metal surface, it needs some energy. So that energy is called work function. So if the energy of the photon is greater than the work function, then the electron is ejected. If the energy of the photon is less than the work function, electrons are not ejected. Okay. So the total energy of the photon is used in used in two ways. Some of the energy is used as a work function, and the remaining energy is used for the kinetic energy. Okay, so that is why the kinetic energy of the ejected electrons are linearly proportional to the frequency of the incident radiation. Okay, so Einstein successfully explained the photoelectric effect done by Hertz, for which he awarded Nobel Prize. Okay, so the third phenomenon is the classic atomic stability. So as per classical physics, atom consists of positive nucleus and negative electrons. There is attraction between positive nucleus and negative electrons. If there is attraction between positive nucleus and electrons that are revolving around this nucleus in circular orbits, then the electron will come closer and closer to the nucleus, and it will fall into the nucleus because there is attraction between oppositely charged particles, and atoms should be unstable. But we find that atoms are stable. So electron is the electron that is revolving in circular orbits. These electrons are not going to dissipate energy continuously. Okay, if you think of the energy, the electrons are going to lose the energy continuously, and they are going to fall into the nucleus because there is attraction. between oppositely charged particles, then we will not be able to explain why atoms are stable. They are supposed to be unstable. Okay, so following Planck's quanta concept and Einstein photon concept, Bohr's model for hydrogen atom, Bohr proposed his model for hydrogen atom. He argued that atoms can be found only in discrete states of energy. That means emission or absorption of radiation takes place only in discrete amounts h nu, and that results from the transition between various discrete states of energy is possible, and atoms are stable. That is why you have only different orbitals, s and p orbitals, because the energy that can be absorbed by these electrons is discrete. Okay, if otherwise we will not have any stable orbitals, because electron can absorb or emit arbitrary amount of energy. They can jump from any way to any other place. Okay, so but Bohr said that he postulated that energy that can be absorbed or emitted is not continuous. It is only in the form of discrete amounts h. That is how we can explain these atoms, why atoms are stable. Okay. So all these black body radiation, photoelectric effect, and atomic model predicts the particle behavior of radiation. Okay, these three phenomena we have discussed that radiation as we should not treat radiation as a wave, but now we should think of that radiation can also behave like a particle. Write major differences between classical mechanics and quantum mechanics. So this is the 14th question. Classical mechanics describes physics of macroscopic objects, whereas quantum mechanics describes physics of microscopic objects. Classical mechanics, we use Newton's laws to study the dynamics, whereas in quantum mechanics, Schrodinger's equations are used. Here in classical mechanics, dynamics are completely deterministic and future is predictable, whereas in quantum mechanics, dynamics are indeterministic and prediction is impossible. In classical mechanics, matter is treated as particles and radiation is treated as waves. In quantum mechanics, both radiation and matter both exhibit wave-particle duality. So in classical mechanics, energies of a particle are arbitrary, including zero also. But in quantum mechanics, zero is excluded and energies of microparticles are discrete. So these are some major differences between classical mechanics and quantum mechanics. Coming to the next question, differentiate between psi and mod psi square. Okay, so psi is a wave function which will tell us about the matter waves associated with a particle. Okay, and it connects the both particle nature and wave nature, wave function, and it is complex. Wave function is generally complex, having real part and imaginary part. Okay, so this is wave function. And wave function itself does not have any physical meaning because it is a complex quantity. But mod psi square has a physical meaning because it is real. Okay, psi is x plus iy, and psi into psi star, which is mod psi square, is x square plus y square, which is real. And this mod psi square will tell us about the probability of finding the particle, which is real. And this psi square satisfies the normalization condition. That means that if you sum up, if you integrate all the probabilities between minus infinity to infinity in 3 dimensions, you are going to find out that the sum of all these sum of all the probabilities are equal to unity. So this is called as normalization condition. So psi has a physical meaning and it tells us about the probability of finding the particle, but psi square has a physical meaning, but psi itself has no physical meaning because it's a complex. And these are the some of the this is a wave function psi for particle trapped in the infinite potential well in different energy level. It has both positive and negative parts, whereas psi square has only positive, and because it is going to tell us about the probability of finding the particle. So the next question, highlight the conditions for an acceptable wave function. So what are the conditions for an acceptable wave function? Can you define, can any function be a wave function? No. So what are the conditions it should satisfy? So the conditions that a function should satisfy to be called as a wave function are these. So psi must be a continuous and single valued everywhere. if you are going to define a function as wave function, it must be continuous and single value everywhere. And its derivatives, dou psi by dou x, dou psi by dou y, and dou psi by dou y. The derivatives of this wave function must also be continuous and single value everywhere. And this wave function must be normalizable. So if you integrate all these, if you integrate mod psi square in 3 dimensions, mod psi square dx, dy, dz, it must be equal to 1. Okay. So these are the some of the conditions that must be satisfied by a function to be called as a wave function. Coming to the 17th question, derive the expressions for eigenvector and eigenfunction of a particle confined in a potential square well. Okay, so eigenvalues, I've been telling this. So eigenvalues are nothing but the energies En, and eigenfunctions are nothing but wave functions psi n. So we need to derive the energies En and wave function psi n for particle trapped in an infinite potential well that we have just now discussed about it. Okay, so we need to solve the Schrodinger wave equation in one dimension. So x is equal to 0 and x equal to a. So the length of the box is a and a particle is trapped in this box. Potential is 0 inside and potential is infinite at the boundaries. Okay, so we need to solve the Schrodinger wave equation to find or to show that the eigenvalues and to find out the expression for eigenvalues and eigenvectors. So this is the Schrodinger wave equation in one dimension. First we are going to start with potential is 0 inside and we are going to get this equation because v is equal to 0. Then the solution of this equation is written as psi of x is equal to a sin kx plus b cos kx. We need to find out this unknown constant to write down the equation completely, wave function equation. So to find out these wave function unknown constants a and b, we are going to use the boundary conditions. So boundary condition says that the wave function must vanish at x equal to 0 boundary and x equal to a boundary. Whatever the wave function can be inside is fine, but it must be 0 at the boundaries because the potential is infinite at the boundary. Okay, so using the boundary condition 1 and boundary condition 2, wave function psi of x is equal to 0 at x equal to 0, psi of x is equal to 0 at x equal to a. So these are the two boundary conditions. So substituting these boundary conditions in equation 4, we find psi of x equals 0 at x equals 0, a sin k is 0 plus b cos k is 0. Cos 0 is 1 but sin 0 is 0. So we are going to end up with b is equal to 0. Second boundary condition we are going to substitute in the equation. So psi of x equals 0, a sin ka plus b cos ka. But b is already 0, so b term is not there, only a sin ka is equal to 0. A sin k is equal to 0 means a can be 0 or sin k can be 0. We cannot take a as 0 because a and b are zeros means wave function is not there. Wave function is 0, which is not true. So we are going to take sin ka is equal to 0. Sin ka is equal to 0, that means sin of x is 0 for the values of x equal to n pi, that means x equal to k. Okay, x equal to n pi, x is actually ka. So ka is equal to n pi or k is equal to n pi by a. Okay, so by substituting this in the wave function equation, we are going to get psi n of x as a sin n pi by a into x. So we are going to differentiate this equation twice. When we differentiate the equation twice, we are going to end up equation 6. Comparing this equation and equation 3 here, I am going to get these two terms. Okay, so from this I can find out the values of energy, which is n square h square by 8 mv square. So we have calculated or we have find out the expression for energies. Next, I need to find a in this equation of wave function. To find a, I am going to use normalization condition. This is because the particle is trapped in one-dimensional box. I am going to integrate the wave function mod psi square dx in one dimension. Okay, so psi of x is given as a sin n pi by a into x. Okay, so I am going to substitute this psi square will be a square sin square. So psi square is a square sin square n pi by x into dx equal to 1. So I am writing sin square as 1 minus cos 2. Okay, so I am writing sin square x as sin square x is equal to 1 minus cos 2x by 2. Okay, so 1 minus cos 2x by 2 dx. Okay, so if I write the integral, separate out the integrals, then what I'll get is 0 to a dx minus 0 to a cos 2n pi by a into x dx must be equal to 1, and there is a square by 2. Okay, so integral dx is x and integral cos 2n pi by a into x is a by 2n pi into sin 2n pi by a into x with the limit 0 to a. If I substitute the upper integral in x, what I'll get is a square by 2 or a minus 0, and the second integral a square by 2. When I substitute a here, in this term a will cancel out, I'll get sin n pi is 0. Okay. Next lower limit 0, so when I substitute 0 here, sin 0 I'll get 0. Okay, so the second term is 0 basically. So what I'll end up is a square by 2 into a is equal to 1. So from this I am going to find out the value of a, second unknown constant. Once I know the value of a, then I am going to write the wave function. So a is square root 2 by a, and the psi of x is square root 2 by a into sin n pi by a into x. So these are the eigenvectors and these are the eigenvalues. Next question is, why matter waves are observed for particles of atomic or nuclear size? Okay, very important question. Why matter waves are observed only for smaller size particle? Why not for heavier objects? Okay, so matter waves are associated with only microparticles. We can understand this by using the de Broglie equation where lambda is equal to h by mv. That means lambda is inversely proportional to mass. For smaller microparticles, mass is small, lambda is large, which we can detect. But the heavier object m is large, lambda will be small. We cannot detect such smaller wavelengths. That is the reason why wave behavior is significant for microparticles, whereas wave associated with macro bodies cannot be detected because lambda is inversely proportional to mass. 19th question. Explain the concept of phase velocity and group velocity. Deduce a relation between them. Okay. So what is the phase velocity and what is the group velocity and what is the relation between these two? That is what we need to derive. Okay. Every wave propagates with its own velocity called phase velocity. If you take any single wave, where this wave has a velocity which is called as phase velocity. Now, in a wave group, but now I have a wave group, if the velocities, I do not have a single wave now. So this is the case of the single wave which has a phase velocity. Now I have a wave group, for example. I have a wave group. In this wave group, if the velocities of the waves are same, all the waves are having same velocity, then I can call the velocity, the wave group velocity as common phase velocity. Okay. Next, if the velocities of these waves in the wave group are different, each wave has a different velocity. For example, this wave has like this wave has like this wave has another wave. So then if each wave has a different velocity, then I cannot call the wave group as a common phase velocity. Then I am going to say that there is a group velocity. The wave group has a group velocity. Okay. When we have a group velocity, then the situation is called dispersion because each wave has its own velocity. The phase velocity varies with wavelength. The different individual waves do not proceed together, and this situation is called dispersion. As a result, wave group has a velocity different from the phase velocities of the waves. Okay, the wave velocity of the wave group is going to different from the phase velocity, and that is called as group velocity. Okay, so phase velocity is a velocity of a single wave. Common phase velocity is the velocity of a wave group, but where all the waves have same velocities. And a group velocity is also velocity of a wave group where each wave has its own velocity. Now we can so we can understand this. So we can understand this by considering two waves of different velocities. So wave 1 is a cos omega t minus kx, and wave 2 is a cos omega t plus delta and minus k plus delta k. So there is a small difference between these two waves. By combining these two, the resultant of these two waves, we can find out that the velocity is not same of these two waves. So the group velocity is different from the phase velocities of the two incident waves. Okay. And so that is what we can show using these mathematical equations of the two waves y1 y2, and the resultant of y1 plus y2 is y, which is this. Okay, so this wave has a phase velocity. From this we can write down the phase velocity as omega by k. Single wave has a phase velocity omega by k, but the group velocity is delta omega by delta k. Okay, so using these equations we can deduce a relation between phase velocity and group velocity. Right? To deduce a relation, we are going to start with the phase velocity Vp. Phase velocity is v into nu into lambda. Okay, so nu into lambda. So I can write this nu in terms of angular frequency omega by 2 pi, and I can write lambda in terms of wave vector k is equal to 2 pi by lambda, or lambda is equal to 2 pi by k. Okay, so by substituting these two, this and this in this equation, so Vp will be omega by 2 pi into 2 pi by k. So 2 pi to pi will cancel out. I'll get omega by k. Or if I want omega, so then k into Vp, phase velocity is this. Now, so I'm going to use this. This is the equation. I've used the equation for phase velocity to get this angular frequency. Now I'm going to use group velocity. Okay, so Vg I know as d omega by dk. But now from the phase velocity equation, I know what is what is omega. So d by dk into omega. So omega is nothing but k into Vp, phase velocity. So I am going to differentiate this product k into Vp. So the differentiation of this is, first we are going to differentiate dk by dk is 1 into Vp plus k into dVp by dk. Okay, so Vp plus k into dVp by dk, so that is phase velocity. Now, so I know that k is equal to 2 pi by lambda. So I know that k is equal to 2 pi by lambda. So I am going to differentiate this k. So dk will be minus 2 pi by lambda square into d lambda. Okay, so now I am going to take d by dk. I want to calculate d by dk. D by dk will be what? K is 2 pi by lambda. And dk will be minus, so that will be minus, there is a minus lambda square by 2 pi into d lambda. So lambda will cancel out, 2 pi will cancel out. What we get is minus lambda into d lambda. Okay, so in the equation 2 I am going to substitute this k by dk, which is minus lambda by d lambda. Okay, so somewhere, yeah, so lambda square, so d lambda is here, lambda by d lambda. So I'm going to substitute here. So Vg is equal to Vp k by dk. So k by dk is minus lambda by d lambda. So basically that equation will be Vg is the group velocity. Vg is equal to phase velocity Vp minus lambda into dVp by d lambda. So this is the relation between phase velocity and group velocity. So we have defined what is phase velocity and what is group velocity. And then we have deduced a relation between the phase velocity and group velocity. Okay, so the last question in part B is that derive the equation for energy of a particle confined in one-dimensional infinite square well and explain energy quantization, 0 point energy and spatial nodes. 0 point energy is nothing but the energy we get. We already know, we have already derived the energies which are called eigenvalues. So that is n square h square by 8m a square. So 0 point energy is called as the ground state energy, which is n is equal to 1. So n is equal to 1, we have E1, so which is h square by 8m a square. Okay, so that is the ground state energy, and spatial nodes are nothing but the wave function. So basically here we have to show the energy quantization, that means energies, and the spatial nodes we are going to find out the wave function psi n, which is square root 2 by a into sine n pi by a into x. So we have already derived this equations twice or thrice. So I am just going to walk through this derivation. So again, particle that is trapped in an infinite potential well, potential is 0 inside and potential is infinite at the boundaries. Okay, and the length of this box is a. So for this particle that is trapped in this infinite potential well, we are going to solve the Schrodinger wave equation. And once we write this, once we take v is equal 0, substitute v is equal 0 in the equation, you get this equation. This is second order differential equation, and solve this second order differential equation. You will get the solution psi of x. A is equal psi of x is equal to a sin kx plus b cos kx. You have a and b as unknown constants. We use periodic boundary conditions to find out b and k, then write the wave function equation, differentiate it twice, compare this equation 6 and equation 3 to get the eigenvalues or energies that are discretized, which is En is equal to n square h square by 8m square. Then to find out the wave function, to remove this unknown constant a in wave function, I am going to use normalization condition. Using this normalization condition of wave function, I am going to find a, and then once I substitute in the wave function, I am going to find out the eigenfunctions or wave functions. Okay, so then we can plot the wave functions and its probability density mod psi square versus x, and we can show that the probability is maximum in the center of the box for n is equal to 1, and probability is maximum at the 2 points for n is equal to, and at 3 points for n is equal to 3, and so on and so forth. Okay, so this is the spatial wave function. We can find out this. We can say that the spatial nodes. Okay, so we have shown, we have proved this. So we have answered the question that we have calculated the energy, explained the energy quantization and 0 point energy n is equal to 1, and we have shown the wave functions are spatial nodes. Yeah, so these are some of the textbooks and references books, and to summarize, I have discussed I have answered different questions in part B, which is long answer questions of module 2. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.